In this class we can see about another important topic in the wireless communication concept. So this topic is called free space propagation model. So we have already seen about the basic concepts belong to the wireless communication, and there we have seen without a wired media we can able to transfer the information from one place to another. Also we have seen that in order to transmit the information we need antennas. So with the help of the antenna, one we say that is at the transmitting side, another antenna we keep at the receiving side. We broadcast the signal and the signal will be radiated with the help of the transmitting antenna, and it will be propagated, and in the receiving side with the help of another antenna we will try to receive. So this is a normal way of having the communication in the wireless media. So now with the inclusion of the word that is free space, we can see about a propagation pattern. So we know that the information is now transmitted and getting propagated through the wireless media, that is air media. So now in order to predict, in order to find the strength of the transmitted signal, what we do, we will try to predict the signal. We will try to estimate the signal power at one place from the transmitter. So for this we will now consider some variables. So in this topic we can consider that we need one transmitter antenna, we need one receiver antenna. Then what we need is we will be using the proper propagation patterns so that we can able to maintain the signal transmission proper way. So what here we consider is in the free space propagation, the media is air media, and also we are having a line of sight path. We are having a line of sight path between the transmitter and the receiver. So the transmitter receiver separation is being identified by a particular alphabet, that is D. So D is the distance separation between transmitter and the receiver. Then when we want to estimate the path loss at a particular area from the transmitter, when you want to check the signal power, then we can able to know how much is the attenuation, how much is the loss. So the signal attenuation is a positive quantity measured in decibel, and from checking the path loss we can able to say that how much is the transmitted power, how much effective is the transmitted power, and in that how much is being received. So transmitted signal, received signal, so the amount at which we have transmitted and the amount at which we have received. And also in this topic we normally take into account the power density. So power density at a particular surface area. Power density is a measure of the amount of power per unit volume. So in a simple term we can say power density is a measure of the amount of power per unit volume. And the next thing which we need to consider here is what is the type of antenna we are using now. So the type of antenna which we are using now is isotropic. So isotropic radiations here we are considering, and the speciality with the isotropic antennas are it actually maintains a constant gain in all directions, and also we will get spherical radiations. The radiation will be spherical, so that the gain will be constant in all direction. But when we say that the most widely used dipole type of antennas, only in a particular direction gain will be maximum. Only in a particular direction gain will be maximum. So now we move to the free space propagation model. So here we can say that the free space power received by the receiver antenna separated from a radiating transmitter antenna by the distance small d can be given by Fry's free space equation. So from the Fry's equation we can able to check out the transmitter power and also the received power. So it states that PR of t equal to Pt Gt Gr lambda square divided by 4 pi the whole square d square L. So here in this expression you can find Pt is the transmitter power of the transmitting antenna, PR of d is the received power after the distance small d, then Gt is the gain of the transmitter antenna, and Gr is the gain of the receiver antenna, and L we consider as a term for loss. So here there is no loss in the propagation, so the value will be taken as L equal to 1. So L equal to 1 indicates that there is no path loss, there is no loss in the transmission. And then lambda is wavelength in meters, because since we are using the antenna aperture is having a relation with the wavelength, that is lambda. So here in this expression we can say that there is the received power will be increasing based on the transmitter power, or based on the transmitter gain, and based on the transmitter receiver gain. So when these values are increased, then we will surely get increased our power, that is we can able to have a good signal power at a particular distance. The gain of the antenna is actually related to the aperture. So effective aperture here considering the gain or deciding the gain, and this effective aperture we are considering for the receiver antenna based on its size. So when the antenna aperture size is more, it's big or large, then we can say the gain is also increased. And lambda is related to the carrier frequency, so we write as lambda equal to C by F, whereby we can say like that is it can be simplified as that is by its relation carrier frequency in hertz, then omega C for the carrier frequency in radians, and lambda equal to C by F. From this we can say C is the speed of light in meters per second. Then here we are using the isotropic radiator. The benefit of the isotropic antenna is it radiates a signal in all directions in a spherical way. So here we take that the gain is unity or uniform, and so the effective isotropic radiator power can be written as EIRP equal to PTGT So effective isotropic. Why we are using the word effective isotropic means we are considering the isotropic antenna. And when you want to write this as including the antenna gain according to isotropic, write in a normal dipole type of antenna. So when in the practical situation we will be more likely to be using with that is dipole based of antenna, so we can say DBD, and for the isotropic we can say that is DBI. Then path loss. So path loss, here we say that is the loss in the signal loss, signal attenuation, and this is a difference between effective transmitter power and the received power, transmitter and received power. So which we can write by the simple expression PL of dB in decibel, PL for path loss, so 10 log PT by PR. So when we put on that expression here, it comes as minus 10 log GT GR lambda square divided by 4 pi the whole square D square. So if antenna gains are not included, then the same expression will become minus 10 lambda square divided by 4 pi the whole square D square. Then for the Fry's equation to hold the distance D, that is the distance we consider here from the transmitter antenna, will be around far field. So the far field transmitting antenna is defined as the region beyond the far field distance, that is DF. Therefore we can write DF is equal to 2D square by lambda. So here D is the largest physical dimension of the antenna, and small df, that is the far field distance, will be much greater than the physical dimension of the antenna. So hence from all this we can able to take the term, that is we need to consider the reference distance or reference point, that is from the transmitter at one place, and that particular distance we are considering as a D naught, that is a reference point. Then we continue the analysis with the inclusion of this reference point from the transmitting antenna. So that content we will do on the next class. So that's all for now. So we can continue the topic in the next lecture.